14.46, the following data were collected at a certain temperature for the decomposition of sulfur chloride, a chemical used in a variety of organic synthesis. Make a graph of concentration versus time and determine the instantaneous rate of formation of CO2 using the tangent to the curve at t equals 200 minutes and t equals 600 minutes. All right. So what we're looking at here is CO2, Cl2 is going to be decomposed into CO2, SO2, and Cl2. All right, they want us to make a graph, and they told us what they want on the x and y axis, so that makes our life pretty easy. Time is on the x-axis, and that's given in minutes. And then they want the concentration of the sulfur chloride on the y-axis. So SO2, Cl2, concentration, and the units for that are going to be moles per liter. All right, and then basically what they do is they just plot the data points given in the book, and so it's going to look something like this. For specific details, you can refer to the back of the book, but essentially that's what it's going to be. And so they want to know what the time, or what the constant, they want to know what the instantaneous rate of formation of CO2 using the tangent line at the curve at t equals 200 minutes and t equals 600 minutes. And so basically we'll just like pretend here this is just a model, 200 minutes and 600 minutes. And basically what you're going to do is you're going to plot this, and you'll have a linear graph, I guess, kind of like so. And what you're going to do is you're just going to take the slope at 200 minutes and at 600 minutes. And so the slope is going to be your answer. Again, feel free to refer to the back of the book because it plots it out in more specific details, but that's pretty much it.
Okay, 14.48. In the reaction between hydrogen and nitrogen that yields ammonia, how does the rate of disappearance of hydrogen compare to the rate of disappearance of nitrogen? How does the rate of appearance of ammonia compare to the rate of disappearance of nitrogen? So the reaction that they give us, the balanced reaction, is this. 3 moles hydrogen, 1 mole nitrogen yields 2 moles of ammonia. So this is a really, really easy problem. All it's asking are the ratios. So for how many moles of hydrogen that disappear, how many moles of nitrogen disappear. It's really just the coefficients. So 3 moles hydrogen disappear for every 1 mole of nitrogen that disappears as the reaction proceeds. And then it also asks for what the ratio of nitrogen to ammonia. So for every 1 mole of nitrogen that disappears, you get 2 moles of ammonia appearing in the reaction. So it's just asking for those ratios. You can pull them right out of the balance equation.
In the combustion, 14 0.50. In the combustion of hexane, a low boiling component of gasoline, it was found that the rate of reaction of hexane was 1.2 moles per liter per second. They asked for the rate of the reaction for oxygen, the rate of reaction for carbon dioxide, and the rate of reaction for H2O. So we start off just with the balanced equation, which is all right, and so they tell us the rate of reaction for hexane is is equal to 1.2 moles per liter per second. And they want to know what the rate of the reaction for the oxygen, for the carbon dioxide, and for H2O. And so the key to this is we're going to use the rate of reaction for hexane, and we're going to be able to find the rate of reaction for oxygen, rate of formation for carbon dioxide, and rate of formation for H2O just by using the mole-to-mole ratio in the balanced equation. So for instance, for oxygen, we'll use what they give us, 1.2 mole per liter per second. And this is for hexane, so, and just a dimensional analysis. For every, there's going to be 2 moles of hexane for every 19 moles of oxygen. So just multiplying across there, we get 11.4 moles per liter per second. And we're going to do the same sort of thing for carbon dioxide. So CO2, using the rate of reaction that they gave us. In this case, there are 12 moles of carbon dioxide for every 2 moles of hexane, so 12 CO2 for 2 moles of C6. I guess mole. And multiplying that across, we get 7.2 moles per liter per second. And last of all, for H2O, um, 14 moles of H2O for every 2 moles of hexane. Multiplying that across, we get 8.4. And that's how you do it.
Okay, this is 14.52. It says, consider the reaction. below. And then it wants us to express the rate of the reaction with respect to each of the reactants and products. And then it wants to know if the instantaneous rate of reaction with respect to HCl is 0.029 moles per liter per second, what is the instantaneous rate of the reaction? So, first of all, just write out the reaction. Okay, so there's the reaction. The two equations in the book that we're going to use, kind of, for this problem are this one, where first it's just saying for any generic problem, you're going to have a coefficient A and a compound A, coefficient B, compound B, yielding coefficient C, compound C, coefficient D, compound D. So there's just any generic equation. So like, for instance, in this case, our little b is going to be 3 and our big B is going to be that. And it's saying that in that case, the rate is equal to negative 1 over the coefficient, so in that case A, times the change in concentration of the substance over change in time. And then also that's going to be equal to negative B, change in B, change in time, etc. Same for C and same for D going on. So for this equation, we plug it in here. It wants to know the rate with respect to each of them. So we would be saying that the rate is equal to, for this one there's no coefficient, so it's just going to be the change in concentration of CH3Cl over our change in time. But when you have, when you're looking for instantaneous rate, if any of you have taken calculus, then you'll understand this a little bit better, but just for everyone else, whenever you're talking about comparing rates and changes in things like this, when you want to know what is instantaneous, you're going to be looking for what the rate is as this change gets closer and closer and closer to 0. So at an instant, as opposed to between 2 moments in time. If you're looking at the change at the rate as the change approaches 0, you're looking at, that's the instantaneous rate. So when you're doing stuff like that in calculus, you write it as d, so it's taking the derivative. So this can also be written as d dt of this concentration, which is what the answer in the back of the book says. I know it's probably kind of confusing if you haven't taken calculus, but that's what that means. Really, it's just another way of writing this. So then for the next part in the equation, you're going to have d dt. This has a coefficient, so we're just going to plug it in just like we do in here. It's going to be negative 1 over 3 of our chlorine concentration. Then that's going to be equal to d dt, no coefficient, so just change in concentration, and that's going to also be equal to d dt. We have another 3 here, so it's going to be negative 1/3 of hydrochloric acid concentration. So that's the answer for part A. It's just this equation right here. It's just comparing the rates, the instantaneous rates of reaction for each of the compounds. Now for part B, it just wants to know if the rate for hydrochloric acid is equal to if this is equal to 0.029, then what is the rate of the whole reaction? So all you have to do is plug that in to here. So it's going to be negative 1/3 of HCl. So that's going to be negative 1/3 of 0.029, which is going to give you 0.0097, or 9.7 times 10 to the negative 3. That's another way of writing it. And that's going to be in moles per liters per second, because it's a rate. So that was kind of confusing, but that's the answer.
(14.54) Estimate the rate of the reaction. This one written out right here. Given that the rate law for the reaction at 0 degrees Celsius is as follows: rate equals 5.0 liter per mole per second times different concentrations. The reactant concentrations are as follows, given right here: 2.0 times 10 to the negative 2 molarity, 2.0 times 10 to the negative third molarity, 1.0 times 10 to the negative third molarity. So basically what they want us to do is come up with the rate, the rate of the reaction, which is really easy. This is just going to be a plug and chug, because they've given you all the information that you need to know. So rate of the reaction, this is what we want to know. And so they've given us the different concentrations. So we're just going to plug these values into this equation that they gave us. And essentially you're just going to multiply through. And when you multiply all of that out, you'll end up with the rate equals 2.4 times 10 to the second moles per liter per second. And that's the answer. That's the rate. Again, really simple. Just take what they've given you and plugging it into the equation.
Okay, this is 14.56. The oxidation of nitrogen oxide, which is released in small amounts in the exhaust of automobiles, produces the brownish red gas, NO2, which is a component of urban air pollution. This is the equation for it, right here. The rate law for the reaction is this, right here. It's also spelled out in the problem in the book. And then in the book, it tells us what the K is, and then it asks us what would be the rate of reaction if the concentration of NO is 0.001 moles per liter and the concentration of oxygen is 0.034 moles per liter. So this is just like number 54. You're just going to be plugging things in that they gave us in the problem. So the rate is going to be equal to, rate's what we're trying to find out. It's going to be equal to the K, which they tell us in the problem is 7.1 times 10 to the 9th liters squared per moles squared per second. Then they also give us the concentrations for these. We're just going to plug them in. The concentration of NO2 is 0.001 moles per liter. That's squared, because that's what it is in the rate law. And the concentration of oxygen is 0.034 moles per liter. So when you look at it, here we have this square is going to come through and also affect the units. So really you have liters squared here. You bring that in, so that's going to cancel out. And here you have mole squared, so that's going to cancel with this mole squared. So then in the end, we're going to be left with moles per liters per second, which is what we want our rate to be in. So that's how we know that we're on the right track here, is when we know that our units are all canceling out correctly. So then when we plug all this into a calculator, we end up getting 241.4, or if you want to be correct with your sig figs, that's also 2.4 times 10 to the second moles per liter per second.
.58. The rate law for a certain enzymatic reaction is zero order with respect to the substrate. The rate constant for the reaction is 6.4 times 10 to the second molarity per second. If the initial concentration of the substrate is 2.75 mole per liter, what is the initial rate of the reaction? So in this, in the book, they give us the initial substrate concentration as well as the K value. And they said that K is equal to 6.4 times 10 to the second mole per liter per second. And for any given equation, we know that the rate law is equal to K times the substrate concentration. So in this case, they tell us that it's a zero order. And so when they tell us it's a zero order, then we know that the exponent for the rate law, because usually it's like n to some number, but in this case, it's 0. So basically anything to the power of 0 equals 1. So in this case, the substrate raised to 0 is 1. So we know that this value right here is just going to equal 1. And then our rate is just going to equal the K value times 1. So K value, which is 6.4 times 10 squared mole per liter per second, times 1. And so then we know that our rate is just going to be that, again, 6.4 times 10 squared molarity, moles per liter per second. And that's the answer.
Okay, this is 14.60. It says the following data were collected for the reaction N plus N yields P plus Q. Then it has a table that gives us initial concentrations and initial rates of reactions for three different reactions of this experiment. And then it wants us to find out what is the rate law for the reaction and what is the value of the rate constant with correct units. So it wants to know the rate law, which is just the equation, and then it wants us to know also the rate constant, which is K. So the reaction is N plus N yields P plus Q. The table that gives us the way that we end up with the rate law is by looking at the equation. So we know that the rate law is going to be rate equals K, and then concentration of our reactions. So it's going to be concentration of N to some number, and concentration of N to some number. Well, I'm not going to use N and M because we're already using those. And just some number X, Y to some number Y. So to finish our rate law, these are what we're trying to find. And we can use the table that they gave us to get that. So all we have to do is compare the way that the rates, the way that changing the concentrations changes the rate in the table. So if we look at the first two, in 1 and 2 on the table, our concentration of M doubles, so is multiplied by 2 between numbers 1 and number 2. It goes from being 0.01 to 0.02, right? And then the rate in those two also gets multiplied by 2. So that will tell us something. And if we also look at between numbers 2 and 3, where N changes, our concentration in N is tripled, so it's multiplied by 3, and our rate between 2 and 3 is multiplied by 9. So there's a really great table in the book. I believe it's table 14.4, but it tells you for like how concentration changes compared to how rate changes, what the coefficient is. So it says in there that when your concentration is multiplied by 2 and your rate is multiplied by 2, that's a first order reaction. So your coefficient is going to equal 1. So we know that x is 1. And it also tells you that if the concentration is multiplied by 3 and the rate is multiplied by 9, that your coefficient is equal to 2. But you don't really need that table to know, you don't need to memorize or anything to know that. You can just look. So 2 to the 1 is 2. 3 squared is 9. So, and that would work for anything. If it were, for instance, a 2, if this had been doubled and then the rate had been multiplied by 4, so it would have been 2 because 2 squared is 4. So you don't have to have that table memorized, but just in the beginning, before you get the hang of that, that's a good helper, I guess. So now that we know the x and y, the coefficients, we know that we know what the rate law is. So let's just go ahead and plug those into our rate law. So that's just 1, I'm not going to write it, and this is just 2 squared. So then the next thing that it asks for is for us to find the rate constant, which is k. To do that, we're just going to take the numbers from one of the steps in the problem. So I just chose to take the numbers from the first reaction and plug it in to this rate law. The first thing I'm going to do actually before I plug things in is I'm just going to use algebra to manipulate this rate law so that it's already equal to k. So when you just divide the rate by both the concentrations, you get k isolated by itself. So k is going to be equal to rate over concentration of m times concentration of n squared. So I'm going to use the concentrations from step 1 in the table. So, and I'm going to use the rate from that too. So it's going to be 2.5 times 10 to the negative 3 moles per liter per second. And then it's going to be 0.010 moles per liter times 0.010 moles per liter squared. When you plug all that into a calculator, you end up getting 2,500, or keeping with sig figs, 2.5 times 10 to the third. So that's the number for k. Now k is the value that has like the crazy coefficients, or not coefficients, the crazy units. So it wants you to have correct units in your answer. So what you need to do is figure out what units are going to be left over when you, through multiplying this. That's why it's really important to write your units out when you're writing the problems. So you have to think of these as being squared. So when you do that, you're gonna end up with this moles canceling, these liters canceling, and then so you're gonna have moles squared, seconds on the bottom, liters squared on the bottom, and moles squared on the top. So, so you end up with moles squared. Yeah. Yeah. Per liter squared seconds. So that's your units for your K constant. So we got our rate law up here, we got our K here. So after you plug in the K to the rate law, then that's the rate law altogether. And that's what it's asked for.